Okay, I'll give a take-home exam on Thursday, and I'll give you Tuesday and Thursday off next week. Okay, but I will be back actually Wednesday, so you can turn in the take-home exam on Thursday. Okay, Thursday afternoon, I suppose, if you want to take more time for it.
What about Tuesday?
Yeah, what about Tuesday?
What?
The week after. Tuesday.
Oh, you want that?
Yeah.
You can turn that in with a lower grade if you want to. I think it's 10. That out. So are there any questions so far for the course? Okay, if not, then we go and treat a spherically layered medium. So we figure out how to treat this using the bipotential. And then we know how to treat the single interface problem. We went through the exercise of deriving the solution for this one. Okay, and using a similar technique, you can derive the solution for this problem as well. If you have incident wave, reflected wave, and a transmitter wave. This transmitter wave will actually be a Bessel wave, because if it gets transmitted as a Henkel wave, when it hits the origin, it will bounce back and give you a standing wave here. So this is also treated in the book. I wouldn't go through that. And then using similar idea, you can treat this kind of problems as well. Okay, and then you can have this kind of problem, and then you can have extension to as many layers as you want. Okay, I won't go through the detail of how to treat this problem. And you can also treat this problem using similar ideas, okay, that you have done for layered medium. I won't go through the detail. Then the question is, what do you do, say, when you have a point source? A point source outside the spherically layered medium. Then you would have to learn how to expand the point source in terms of spherical harmonics instead of plane waves, because now we know how to propagate spherical harmonics with the bipotentials and spherical harmonics. And spherical wave functions, we know how to propagate them. Okay. And so the key thing here then is to how to expand the point source in terms of spherical harmonics. And I can give you the answer for that, but I won't tell you the detail on how to find them. Okay, so if you have a point source, it generates a spherical wave in this manner, which is the Green's function. Okay, and this turns out to be the spherical Henkel function of the first kind of the zeroth order. Okay, that's why I say when things are in spherical coordinates, they are very simple. And you can go through the same procedure of expansion and so on, and then you can show that this is equal to spherical harmonic function in this manner. Times the spherical Bessel function, r less than, I'll explain to you what r less than is in a moment, spherical Henkel function of the first kind of nth order r greater than, and then Pnm cosine theta Pm, there actually should be a magnitude here, cosine of theta prime e to the I and phi minus phi. Okay, so it turns out the spherical wave can be expanded as such, where r less than is the lesser of r and r prime. Okay, r greater than is the greater of r and r prime. Okay, which means that if you're in the observation point, this is a point source expansion, and the point source is located at distance r prime away from the origin, and then you add a distance r with your observation point, then r less than will take the value of, say if you're over here, your observation point is over here, it's definitely clear that r is larger than r prime, okay, from this picture. R is larger than r prime, and then it's quite clear that then you should put r prime here, r over here. Okay, for this case over here, this expansion will become jnk r prime hn1k r. Okay, that's for this expression becomes that when you have things outside the circle. Yes?
Is that identity known?
This identity, it can be proven, it can be derived. Okay? I will show you, I will tell you how to derive it. I will show you how to derive it. I will tell you how to derive it. And then you can derive it as a homework. Okay? It's quite easy to derive. Okay? So, this is the case. And if it's the other case around, say if your r prime is over here, and then your r is inside here, your observation point is inside. And in this case, it's clear that r is less than r prime. And then this expression here will become jn kr hn1 kr prime. This is the standing wave. This represents an outgoing wave. It means that if you're over here, the wave in region in the outside the circle should be expressed in terms of an outgoing wave. If you're over here, then the wave inside the circle should be expressed in terms of a standing wave. That's what it means physically. So this expression has dichotomous behavior. It's dichotomous behavior, and it's actually a solution to this equation. It's actually the solution to this equation. And that solution can be, this expression can be written in terms of spherical coordinate system. If you write this delta function in terms of spherical coordinate system, it will look something like this. Sine theta, delta theta minus theta prime, delta p minus p prime. Okay. So why is the other function expressed as such? The delta function is expressed as such because if you take this function r squared sine theta delta theta minus theta prime delta phi minus phi prime, if you integrate in the spherical coordinate system, you will have r squared sine theta d theta d phi. This is a Jacobian of integration in the spherical coordinate system. We go from 0 to infinity, theta goes from 0 to pi, and then t equals from 0 to 2 pi. Right? And this should be equal to 1. And that should be equal to delta x minus x prime delta y minus y prime delta z minus z prime dx prime dx dy dz, right? Doesn't matter. Dx dy dz. And both of them should be equal to 1. That's why the direct delta function in spherical full energy system is expressed in this manner. And then you can solve this equation by matching boundary conditions. You solve it by separations of variables, and then you match boundary conditions to match the singularity at the origin. And then you will get this jump discontinuity, and you'll get this expression. And you make use of the orthogonality property of Legendre's polynomial, or Legendre's function. These are Legendre's functions. Okay. Are there any questions regarding the derivation of this? Yes, Junwei.
So how about the case when r equals r prime?
R equals r prime is a tricky case because then the delta function is right at this point. And it's the very tricky case, the same case as what you have found in the Sommerfeld-Weil identity. Okay, if I go back to the Sommerfeld-Weil identity, the same kind of philosophy applies in deriving this using plane wave expansion, which is just double integral e to the I k x x minus x prime plus I k y minus y prime over kz, and then you have another term that helps with the convergence. This is the Sommerfeld-Weil identity. So if you are at the plane that contains the source point, which is at the plane that is z equal to z prime, this integral does not converge. It seems to decay, but not decay fast enough for convergence. When you try to numerically integrate this, it does not converge. It's 1 over k x squared plus ky squared decay. It's not fast enough. And this is not possible. And you can say that this summation does not converge at this point. When r equals r prime, this summation does not converge. But then these two functions are equal to each other. When r equals r prime, these two functions are equal to each other. So the potential is continuous across this surface, but the derivative is continuous. The representation by this can only be understood in a distributional sense. Just like when I set z equals z prime here, I can still think of this as an identity, but only in a distributional sense, because this thing actually does not converge. Very much the same way that I can often write delta x is equal to 1 over 2 pi dkx e to the I kxx. This thing actually does not converge, but I take this as an identity in a distributional sense. Okay, they don't converge, but these are equal to each other in a distributional sense. So this does not converge when z equals z prime, but this can also be treated still as an identity, and you can also treat this as an identity. Okay. So once you know this identity, then you would know how to solve this problem. You would be able to express the vector wave in terms of spherical harmonics, and then solve this problem. And a lot of it is very complicated, but quite straightforward. Okay, very complicated, but quite straightforward. Are there any questions regarding this? How you will solve the problem of a point source in a spherically layered medium or outside a spherically layered medium? But this is the key identity. This is the key identity. This is also called the translational addition theorem, because I'm actually expanding a wave that is actually emanating from this point source in terms of waves that are emanating from this source over here, okay, or a standing wave over that point. This is also called a translational addition theorem. important for the fast multiple algorithm. If you need to study the fast algorithm, you need to understand this identity or this addition theorem. And it's called translational addition theorem because it came from the addition of angular momentum in quantum physics. When you add two angular momentum, two angular momenta, you actually have a lot of formulas that look like that, coming from the addition of angular momentum. But this is just a simple example where you see this again. Okay? So are there any questions regarding this? The other mathematical techniques in physics related to waves in a spherically layered medium, I wouldn't go into them in detail, but I just want to tell you about them. Okay? I want to tell you about them. And then the next question is, we did a lot of this for planarly layered medium, which is extracting ray physics from wave physics. We started to see ray physics emerging when we apply asymptotic. How do you do this for this problem? It's extremely difficult, but I won't do it. I will tell you how people do it. Okay? So, what they do then is to apply something called the Sommerfeld Watson transform. What you have here is the summation. When you solve this problem of a point source in terms of layered medium, you have something in terms of summation. Okay, the solution would be something in terms of summations of waves or spherical harmonics. And then something rather complicated, maybe a function of r prime. And then with all the spherical harmonics out there. Very complicated. The first thing that needs to be done is actually to convert this into an integral. Integral of some sort. So you have an integral. And then after an integral, you go to do contour deformation. And asymptotic expansion. Like what we did for the planarly layered medium. Okay? And then you start to see ray physics emerging. It's a very complicated process. It takes a lot of mathematical work to do this. But let me see what let me just tell you what the outcome is. The outcome is some important physical phenomenon that you observe in a curved surface. That is that if I have a perfectly electric conducting sphere, if I shine wave on top of it, and then if the frequency is high, I should expect ray physics to emerge. Okay? So one of the things that you see in this kind of theory is specular reflection term that looks something like this. And the wave will be reflected as such, some of them will be reflected as such, depending on where your observation point is. So you start to see ray physics emerging. And then another very important, pretty interesting thing is that you start to see waves creeping around this surface, this curved surface. This would be called a creeping wave. Okay, you will see creeping waves coming around the thing. And then these creeping waves are actually very important in reducing radar cross-section, because if you have an object and if it's of a certain shape and you shine a radar onto the object, you would want as little reflection from this object as possible, so you start coating these things to reduce what is called a backscattering. Backscattering is a part of the radar signal that comes back directly as this at the sensor that sends out the radar signal. But then there will be some waves, no matter how hard you try to code this thing, if you're not careful, there'll be some wave that creeps around and come back to the sensor. Okay, and that signal has to be reduced in stealth technology because you need to cut down this creeping wave as much as possible because it can creep around the thing and so on. But they're usually quite weak. But then the intent of the coating or stealth technology is to make an airplane look like the size of a bee. Okay, that's the story you read in the newspaper. If you are able to coat an aircraft well enough, then you can get the aircraft to be invisible in the radar signature, and it will look like the size of a bee. Okay, but of course, how do you anti that? How do you counter the stealth technology? You switch frequencies, right? You code the thing with certain frequencies, and they only work for certain bandwidth. If you use a broadband signal, the airplane cannot hide itself anymore. So the counter stealth technology is to send in a broadband signal, and no matter how hard you try to code, you will see a signal coming back. And of course, there is a lot of heat, a lot of enthusiasm on cloaking in recent years. Cloaking is also a way of generating stealth technology by using materials around a target. It turns out that you can prove that if you have an object and if you coat things around it in the proper fashion, the light can go around the object as if the object is not there. Okay, by using epsilon, which is inhomogeneous. And if you do that, the light will creep around. So to a person, this object becomes invisible. This is equivalent to the light traveling to the thing, and this thing has been reduced to a point. Okay, reduced to a point by cloaking with inhomogeneous material. But again, this is a very tricky technology to achieve because it might work at a single bandwidth at a certain frequency. You design all the epsilon and mu so that the light will bend, the radar wave will bend around the object, but if you change the frequency, the cloaking technology breaks down. So people are receiving a lot of funding to study this kind of work. But maybe futile, because somebody will find a countermeasure to it anyhow. Okay? So this is just what is happening in the area of stealth technology, but there's another interesting phenomenon called the whispering gallery wave. Okay, this is the opposite of that one. That is, if you have a curved surface, if this is PEC outside, then if you send a wave in, there will be specular reflection, but there will be also a wave that creeps on the inside on a concave surface, and that is a whispering gallery wave. That wave does not decay. This wave has to radiate. This wave that creeps around has to radiate. Okay, it radiates. So it's, in a sense, leaky. Okay, it's leaky. It's leaky, so it leaks energy. But this wave is not leaky. It can creep around and does not radiate. Why does this radiate? Because of the fact that it bends. When you bend a waveguide, like if you have an optical waveguide, you bend it, you will have to leak energy. Because you essentially, if you have a waveguide, if the wavefront is something like this, if you bend it, then the wavefront will have to look something like this. Which means that the kx becomes smaller, right? Kx becomes smaller. If I call this kx, okay, kx becomes smaller because the wavefront becomes further and further apart. If kx becomes smaller, then the k rho, ky, okay, ky is equal to k squared minus kx squared. So ky becomes real and the wave starts to leak. Okay, so we bend the waveguide as a leak. And similar to this notion, this wave that creeps around has to leak because its phase front is moving too fast out there. It cannot keep up with the phase front and then it starts to leak. This one does not. This one will have a phase front that is not leaking, so this thing can propagate a long time. And I guess it was first heard in cathedrals or churches, or that's why they call this the whispering gallery wave of whispering gallery mode. So if you go to the old European churches, they always have this curved wall. And if some monks were plotting against each other on the other side of the gallery, the other monks can hear them. Okay, that was how the story went. But if you want to experience this phenomenon, you don't have to go all the way to Europe. There's a Noel slab over here. When you go to Noel slab, you see an arch. You see an arch outside Noel slab. Chemistry lab, I think, Noel. And if you just stand over here, and then have your comrade stand over here, and just whisper to the wall. And you can see, you can ask the other guy to listen on, and you don't have to talk very loudly, and he can hear you. You can go to the nose lab and experiment with that. I did experiment with somebody before, okay, and it did work, just over here. Or you find any curved surface, there might be some curved building in China or something, it always works as long as you have a concave curved wall. Okay? Any questions regarding this?
What is specular reflection?
Well, specular means directly off a flat surface. This is called a specular. Okay, off a flat surface is called specular.
How is it different from like people say reflection, specular reflection? What's the difference?
Well, specular, this is what they use in ray theory anyhow. This is, I don't know why they start using this word. Okay, anything that goes off a flat surface is called specular reflection. I don't know why. Maybe it has something to do with coherence. I don't know. Because as you learn from your Sommerfeld well identity that if you have a late medium, the wave comes in, if they're coherently reflected, then they give rise to a specular reflection term. Okay, because of wave coherence. Okay. Okay, I guess I'll stop talking about chapter 3 and go to chapter 4 and talk about transients. And you can read up about all those things if you want to. Okay. This is very difficult and interesting knowledge, but it's going to be a lost art. I think a lot of people wouldn't know about this kind of thing in the next generation or so. So I like to talk about transients. This is intimately related to time domain measurement. And many measurements are done in the time domain, like radar is done in the time domain. And what is the advantage of doing measurements in the time domain? I think the best thing that you can get is actually gating. Say if you do an experiment in a room, if you want to study for the scattering from an object, but there are other objects around, and you don't have an anechoic chamber, and you like to only measure the reflection from this object, and if you do this measurement in a time domain, you will have one major reflection plus echoes. multiple reflection from the other objects. And if you do time domain measurement, you can gate out this thing. You just pick up the main signal. And this will be as if you have done this experiment in an infinitely large room or anechoic chamber. Okay, so gating is one reason. Of course, time domain measurement is always done in radar. And you can also gate out different signals from multiple objects in radar quite easily. If you do synthetic aperture radar, those measurements are also done in the time domain. Use gating to classify returns from different parts of the terrain. Okay, you do synthetic aperture radar. So time domain measurements are actually quite important. Many measurements are done in the frequency domain for some good reason. Do you know why measurements are done in the frequency domain in the lab? Say if you want to do accurate measurements, they're usually done in the frequency domain, but not in the time domain. But many practical systems are actually in the time domain. If not in the time domain, in the narrowband domain. Like a radar signal will have a carrier, and then it will have an envelope. So this is quasi-monochromatic in a sense, because you put an envelope and you give the radar signal an envelope so that you can do time gating. Okay? But most measurements in the lab are done in the frequency domain. What is the reason for that? Does anybody have a good reason for why you want to do measurement in the frequency domain? Whereas most practical systems, your radio, your cell phone, your everything that you have is in the time domain, right?
Because you can average out like noise and do a bunch of frequency measurements to reconstruct the sound.
That's right. Very good. Okay. Measurements in the lab, you have the liberty of measuring over a long time. Okay. And because you have the liberty of measuring over a long time window, you can make your measurement as accurately as possible by doing time averaging. That's one thing. By doing narrowband filtering. Okay, narrowband filtering. I think that's a very important concept. Narrowband filtering gives you good signal to noise. Why is that so? Because you know that when you have any electronic system produces noise. And that noise is thermal noise. Okay? If you do any measurements in the lab, you cannot escape from thermal noise because you have to do the measurement at room temperature. Unless you're very rich, you can do the measurement in a cryogenic system and cool down the whole room. Okay, otherwise, all your electronic systems have resistors, transistors, capacitors, and those generate thermal noise. The thermal noise is generated according to this formula. The energy in the noise is roughly 4 kVt times the resistor times the bandwidth of the measurement system. Thermal noise is white noise. Okay, because they're white noise, they distribute themselves almost evenly over the entire bandwidth of a measurement system. And the energy in the bandwidth in the thermal system is roughly proportional to the Boltzmann constant times the temperature times the resistor. If you have any resistance in your electronic system, that will generate thermal noise times the bandwidth. So one way to get rid of the resistive noise, thermal noise, is use superconductivity. If you have superconducting materials, they generate less thermal noise. Of course, it can cool the temperature too. Okay, make the temperature low. So one way to reduce this thermal noise is to make the bandwidth as small as possible. Do narrowband filtering. So you design extremely narrowband measurement systems by heterodyning systems, super heterodyning systems. You probably have to learn how those things work. That you can actually do a microwave measurement at kilohertz bandwidth by heterodyning the system now. And then if you do that, then the noise that comes through your system becomes very small. Okay, becomes very small, and then but if it becomes very small and it's very narrow band, what does it mean? It means that you have to actually measure a system over a long time scale. You have to measure it over a long time scale. If it's kilohertz signal, that means if you measure over a long time scale, you do time averaging, or multi-shot averaging, or averaging over many duty cycles. You can make the measurement system to have as narrow a bandwidth as you want by just measuring over a long time scale. As long as you have a very stable oscillator, local oscillator is very important. The local oscillator has to be stable and actually generate a time harmonic signal over a very long time scale, and you can use the stability of the local oscillator to average out any thermal noise also.
Excuse me, I heard about another chaotic no noise scheme. It's quite the opposite from this mechanism.
Chaotic?
Yes.
Low noise scheme?
Broadband chaotic.
Broadband chaotic. Let me see. How would that work?
What is-
I have heard of a spread spectrum communication system where they try to increase the bandwidth of a communication system by trying to broadcast the signal over as many frequencies as possible. And that increases the bandwidth of the system, but not reducing the noise though. I don't know how you can reduce the noise by increasing the bandwidth and then making it more chaotic. I'd like to learn more about that. Maybe you can tell me someday more about this chaotic system that is good signal to noise as well. Okay. So let's go back to transient. Transient is actually what happens in the real world. Time harmonic is not real. Okay, time harmonic signal is not real, and you always have a certain bandwidth to your system, no matter how constant wave or time harmonic you want to make it. So let's learn about some physics of the transient system so that you can put things in the real perspective. I think one of the things that you should learn about a transient system is a